Okay, so welcome to our first webinar of the spring 22 semester. Um, this one is going to focus on a couple of really neat applications of sort of the pickup. I don't know if you could call it philosophy or mindset or whatever it is that we have to the high school world, and I, for one, am very interested to see how you teach quantum mechanics and data science to high schoolers. So, a couple of announcements before we get underway. One is that this is the first of our pickup webinars for this semester. We have webinars coming up in March and April, so stay tuned for more details on those. Our March webinar, we are trying to coordinate with the Alpha group that's going to talk about how we can combine computation and experiment in what are often seen as theory courses. So that'll more details to come, but that'll be in roughly a month from now. The one other thing I did want to mention, in case you came to this from somewhere else, is the PICUP Slack channel, which is where most of the pickup information happens. So if you head to the PICUP website, there's a big link to join the Slack channel. The Slack channel is a great place to get information, ask questions, see announcements. So check that out. Okay, that's all the yammering I have. I don't know, Brian, did you want to go first? I have you first on my list.
I'm fine going in either order. Maybe Chris and I can rock, paper, scissors for it.
Brian, you can go ahead.
Okay.
I've had
All
a long
right.
day. So.
Chris's project is probably farther along than mine, so it's probably better to do a progress report and then a more complete progress report.
All right, so Brian's going to tell us about how you can teach high schoolers quantum mechanics.
Nick, I have host disabled participant screen sharing, if you don't mind addressing that.
Okay, that should have fixed that.
Okay. All right, there we go. Let me get my screen up here. All right, it looks like I'm in screen share mode. Thanks everybody for coming out tonight. I'm going to talk to you about some work I've done with these wonderful people on delivering some quantum content to high school students using computation. So we've got a little bit of quantum and a little bit of computation going on. No quantum computing going on yet. So it's sort of two separate silos right now. But we have two undergraduate assistants working with us, Julia Whitley and Abby Pruitt, and then Dr. Terry Galanti, my colleague from our College of Education and Human Services. I do want to acknowledge we are supported by a couple of grants from the Voya Foundation and from American Institute of Physics. So what I hope to convince you of in about a minute or so is that we do need to start thinking about how to prepare our students for a quantum infused future. Both at the college level, obviously, that we're already trying to do, but also at the high school level. Then I'll go over the spins first approach that I think some of you are familiar with, but talk about how that sort of eases the entry point for quantum mechanics compared with the wave function first approach. We'll talk about how we use computation to further improve the accessibility, and just like we do at the undergraduate level, to sort of smooth over a lot of the mathematical barriers that can come in the way. And then I'll talk to you about the professional development structure that we used in fall 2021 and that we are relaunching with our new cohort in spring 22. So when we talk about integrating quantum into the high school classroom, we're not just talking about teaching them some interesting, more modern topics in physics. We really are talking about bringing in something that's going to be useful to them. If we think about the careers that many of these students are going to have in material science, nanoscale devices, quantum computing, not just working with those at a research PhD professional type level, but at the sort of sort of everyday mechanic level of, I need somebody to fix my quantum computer. I need somebody to work on the processing or the measurements of these new materials and things. That's really not all that different from how we need today's students to have a background in classical mechanics, right? It's not that we expect every student to come out solving the Schrodinger equation, just like we don't expect every student to come out building a Hamiltonian or a Lagrangian, but we want them to have some familiarity with it so that when they do see it later on, it's not throwing them for a loop. And of course, as we all know, quantum is uniquely challenging with its counterintuitive nature. So our philosophy is let's start early to sort of bring in that, counterintuitive, interesting stuff from quantum. But then, of course, the big question that's going to come to everybody's mind is how do you overcome the mathematical barriers, right? If we're already, sticking to some very simple cases, we're kind of dancing around the calculus in the high school level. How on earth are we going to teach this quantum stuff legitimately with some actual applications if we can't do partial differential equations with a complex wave function? And so we're going to talk about how we do this with a spins first approach to scaffold the entry, to really go to kind of one of the simplest but conceptually accessible problems in quantum mechanics. And then we'll talk about how we use the computation to handle what's left over of the mathematical complexity, literal complexity, because we can't get rid of square root of -1 in a quantum lesson. And then we'll talk at the end about how the students are going to focus on exploring the concepts rather than solving problems rigorously. We use the computation to explore it like an experiment, essentially. So if you're not familiar with the spins first approach, I highly recommend picking up a spins first textbook like McIntyre's text here. This approach is based on a lot of difficulties that students seem to consistently have with the wave function. So for example, students see waves as complicated. Through years of experience, you and I have learned to see waves as a pattern of the number of nodes, the number of antinodes. Is the amplitude consistent or is it changing? But students really see it as a complicated function that's got all these points that they've got to trace out. Also, the fact that we call it a wave function, but psi is not always, or in fact rarely, a sine or cosine. What does that mean when we call it a wave? That's a bit esoteric for them to wrap their minds around. Also, the fact that you're dealing with an infinite dimensional energy space can be a bit intimidating. We like to think of vectors or vectors, but it really is different when you're talking about x hat, y hat, z hat compared with an infinite number of energy stationary states. And also, by the way, your position value is going from -infinity to +infinity. We don't really do that a whole lot at the high school level. It's not really clear how to tie the wave function directly to experiment. We could certainly bring out a paper to show students, look, we're measuring the density of electrons that's proportional to psi modulus squared. But bringing that into the classroom, that's a challenge.
Lay down. It's okay.
And then, of course, there's lots of mathematical baggage coming before you can even get to the cool stuff. So before you can even talk about measurement or the uncertainty principle, you've got to build up all of this calculus, integration, probability stuff just to make sense of the actual physical concepts. On the other hand, when we come to a spin 1/2 system, spin 1/2 is a coin flip, right? Students understand heads or tails on a coin. So if we just kind of paint that picture that it's a two possible state system, spin up and spin down, that's at least conceptually accessible, even if it's a new topic to them. Instead of an infinite dimensional energy space, we've got psi is a two-dimensional vector, which they're already learning about, right? They already know how to deal with a basis set of two vectors. Now it's just one is spin up and one is spin down. This is a lot more directly comparable with experiment because you can help orient students to a Stern-Gerlach experiment or a similar magnetization experiment pretty quickly, with some video demos or some simulations. You can get them thinking along those lines. And essentially all of this combines to let you get to quantum concepts sooner. You can start talking about, you can start talking about measurement causing state collapse or the uncertainty principle or all that cool stuff that you don't really get to envision until later on in a Griffith style textbook. You can get to a lot sooner when you're talking about spin 1/2 because it's a lot faster and simpler to go through. And we hope that this brings less mathematical baggage. It certainly eliminates the need for any sort of calculus or derivatives. But as you're probably imagining in your mind, we've still got to have some complex numbers. We've still got to have some linear algebra, which in principle students can learn in a junior, senior high school math course, but not every student gets to see. And so there might still be some mathematical barriers we have to overcome, even if they're smaller. And of course, as we're all trained to think about it through PICUP, this is where computation comes in. So remember, computation is where we use a computer to facilitate the study of a physics problem. It's not that the computer is taking the place of the math, it's just offloading a lot of the sort of nitty-gritty minutia so that we can focus on the sense making. And so when we talk about computation, we often like to advertise that we can lower mathematical barriers, we can open new problems for study, and we can get past the tedium of solving the same type of problem again to really focus on conceptual understanding. And oh, by the way, if we really want to think about preparing these students for a quantum focused industry, computation is going to be in high demand there. And so in our context, for teaching students a spins first quantum approach, this means using snippets of code that are about 30-something lines long to create these two-dimensional spin states, spin up and spin down. So that's just going to be a 1, 0 or 0, 1 in terms of a column vector. We need to create our 2x2 matrices for S sub X, Y, and Z. And then we need the computer to carry out the matrix math for us so that we can jump straight to the interesting stuff, the probabilities, the expectation values, etc. Still valuable for students, obviously, to do that by hand so that they have some idea of what it means to multiply matrices or multiply a matrix onto a vector. But once they kind of get the hang of that, we can hand it off to the computer so that we can focus on the cool stuff at the end. And so like many of us do with our class activities, we want students to focus on adjusting the thing of interest, psi in this case, to explore the results like an experiment. I accidentally touched my scroll wheel, so let me get back to here. All right, there we are. So the way we're structuring this, we're really focused on providing professional development to teachers. We have not personally interacted with the high school students yet. We've been training the teachers. Basically, our goal is to give them the learning experience that we want them to pass on to the students. So we've written our PD modules in Jupyter Notebook just because it's nice to combine the theory and setup right with the code in the same document. We also provide them with video overviews that we embed in the document. If you want to learn how to embed a YouTube video in a Jupyter Notebook, let me know. I can send you the code snippet. It's a wonderful tool because it just makes it much more interactive. So the goal is for the modules to develop the teacher's content knowledge, because for many of them, if they did a major in physics, it's been a while since they took that quantum class. And of course, we know statistically, most of the high school physics teachers out there don't have a formal physics background. We also want to focus on presenting quantum applications. So we're digging up some popular articles about spin memory storage, quantum computing, all this neat stuff that they can plug directly into their classroom as something that students can understand what's going on. And we spend some time from the literature discussing unique quantum learning challenges like we talked about earlier. We're asking the teachers to complete about one module a month. We're trying to be very flexible and accommodating with the ongoing normalized COVID pandemic. And we meet about once a month on Zoom to discuss what their progress is, what questions they have, what they've been surprised by. And when they complete the full set of modules, they get a stipend at the end, thanks to our funding agencies. We also include some reflection questions that really focus on what the learning process has been like for them and how they would see these materials being of use in the classroom. We have no preconceptions that the teachers are going to take our exact materials and deploy them in the classroom. We're really interested in working with them to adapt these materials, present them in their class, and help them kind of go through the revision process so that these can be as useful as possible to their students. And so what have we seen so far? Well, we've seen a few teachers really like the Jupyter environment. We had 2 teachers participate last semester who they completed all the modules and they immediately went on and learned more Python that they can incorporate into their classes. So we've got one of them working on learning turtle graphics so that he can use that in his geometry class that he's also teaching. So we're really hoping that quantum kind of is the interesting subject, but then they can develop their confidence in the computation to use that in topics beyond quantum. We want to see how adaptable the quantum content is. There are lots of folks trying this out at the high school level, and there's not really a good sense of where the boundary is of what's appropriate for the high school context, what really needs to wait for the undergraduate context. Particularly we want to see how accessible we can make matrices and complex numbers. I know I remember learning about both of those in my 11th grade pre-calculus class, but I also know that that is not the experience of every single high school student that's out there. And what we've observed is that most of these teachers seem swamped by accommodating students for the pandemic. We had a nice cohort sign up at the beginning of the fall, and we had 2 at the first meeting, and they stuck through it. And then we keep inviting the other folks who have signed up. We keep inviting them back, in the chance that they have a month where they're able to devote to this. We do have a new cohort starting now in spring 22. We just had our first meeting for that a couple weeks ago. We've got some folks who are very interested, excited. We originally were recruiting from just our own school district in Northeast Florida. And then I gave a presentation about this at AAPT, and that generated some interest across the US. We've got one person participating from Canada. It turns out physics teachers are very hungry for professional development, because many times when they go to these workshops hosted by their districts, the workshops are primarily focused on biology, because that's where the numbers are. That's where they have the majority of the demand, the majority of the teachers, and the physics teachers just kind of get attached on there, and they try to extend it to their own classroom. But anything that is physics specific, they're always very excited to have. So this spring, what we're doing, we're actually setting up 3 tracks now that we've got our second grant in place. So the folks who completed the intro quantum in the fall are going to continue on to advanced quantum. And now that we think they're ready to graduate to the wave function, so they'll be meeting the wave function in March after they learned about energy levels this month. We are restarting some fall teachers in the intro quantum sequence, so we are repeating that. We've learned from our fall experience that we really need to break these notebooks into smaller chunks. My idea was to just give them 1 notebook a month that they would just whittle away at week after week. That became intimidating. It was hard to keep track of where they were, where they had left off. So we basically splitting those up into smaller notebooks. Anytime there's a logical stopping point, we split it up so that they've got a better sense of accomplishment of where they are. We're also trying to provide more hands-on tie-ins. So things like manipulative, tangible activities that you can do to visualize the wave function. We're also going to try out offering more frequent meetings, still have that big monthly meeting, but then we're also doing a weekly office hour night where they can just drop in for questions. And then we also, based on those interactions we had with the teachers in the fall, we realized that they are interested in doing more with computation than just a single topic like quantum. So we have a generic computational integration. I see Adam Lemia is in the chat. We have gratuitously borrowed his lab data analysis notebook and are walking them through that wonderful activity as a sort of a stepping stone to give them something they kind of already know how to do. And then we're branching off from that into simulation, modeling, visualization, that type of thing. Our goal by the end of the spring is for them to be able to sort of join the streams together and over the summer adapt and create their own activities so that we can hopefully expand the PICUP collection's representation of high school appropriate exercise sets. And then in the fall and spring of next academic year, we'll distribute them to the classrooms. We'll go in and conduct some observations and give feedback so that we can then revise and promote these throughout the community. So technically our spring cohort has started, but like I said, we try to be flexible and adaptive. So if you've got high school teachers who are interested in something like this, feel free to have them reach out to me. We are always looking for folks to join the current cohort. That was about 15-20 minutes, so I think that's a good time to stop there.
All right. We have some time for questions. I guess we should clap in our virtual way. We have some time for questions. Anybody have any questions?
Or my collaborators in the audience. So Terry, if I left anything out, please let me know. Question in the chat, do we get to quantum computing? That's certainly one of the applications that we have, in the sense that, we talk about spend one half, we say, oh, you could use this for building a quantum computer. Here's a link to an article that discusses that. We don't have that as a proper academic activity yet, in the sense we're not teaching them a quantum algorithm. We're not teaching them quantum error correction and all that stuff. I could see us expanding to that in the future, but right now we want to see what we can do with the base set, and then we can formalize the applications more.
Adam's got a question.
Hey, Brian, really awesome stuff. This is probably the second or third time I've heard you talk about the same thing. Maybe probably the same set of slides.
Probably.
But yeah, super cool, super cool. I want to know how long until this starts edging out the traditional Griffiths-based undergrad quantum class.
Okay, so in terms of the spins for structure itself, all due love and respect to the Griffiths textbook. In my mind, not soon enough. Just because I remember when we got to spin when I was an undergrad, and I was like, oh no, now the wave function has this pointy thing around it, and I don't know what that means. And the professor's talking like it's easy. And then once you realize how much simpler it is than the wave function, you're like, oh, well, I could have been doing this all along, I guess. And I think that actually makes it, I think it gives it a little bit more opportunity for interaction as well, because you're able to treat it more like a model. Obviously the wave function is a model too, but it's kind of handed to you as this big esoteric thing that when you first meet it, you don't even know what it's for. And then a chapter later, you get to, oh, here's an expectation value thing you could calculate there. Just being able to treat it as here is a model. It has two knobs. It has a spin up knob and a spin down knob, and the knobs happen to be complex numbers, so really it's four knobs. But just having that simplicity of the system and being able to basically discover things like the uncertainty principle or discover incompatible observables is just so much more powerful than just being handed it and saying, go confirm this. We have a comment in the chat, an upvote for spins first. So yeah, I've taught an undergraduate course with spins first and with Griffiths. I would do spins first any day of the week.
Yeah, seconded.
Yeah.
Okay, well let's thank Brian again. And our second speaker today is Chris Orban from Ohio State, who's going to tell us about teaching data science to high schoolers.
Sure. Can you hear me okay? Great. I'm going to share my screen. Zoom, every 1 in 10 times it will crash when I share my screen. So let's see what happens this time. The desktop 2. Just want to show me the button. Can I have the button to press to go? Doesn't want to do that one. Doesn't want to do that one today.
Chris, while you're getting set up, Brian, I don't know if you're still there, but Ernie had a late question in the chat. Maybe you want to field that one, and if Chris's slides pop up, we'll switch over to him.
The high school students to conceive of spin. I mean, how do I expect me to conceive of spin? That's a good question. I think one good comparison to make, because it's where magnetism comes from, is to just compare it to magnetism north and south. You can give that as like a phenomenological reason for considering it.
Hey, can people hear me now and see me? You can see me in front of the screen and all that. Okay, I'm sorry. Yeah, Zoom, as I predicted, Zoom crashed, but when I open it up again, it worked just fine. So it's one of those days. So Brian and I have many things in common. It's good to see you again, Brian. We don't talk enough. We are recently very happy to have won the American Institute of Physics Meggers Award, which it's an award, but it's a grant to focus on high school physics stuff, and it's one of the few grants I'm aware of that focuses on high school physics. And I have nothing but positive things to say about those folks. And I encourage you all to if you're thinking about working with high school teachers in your area, to consider applying for that. It's every 2 years. So STEM Coding won it in 2017, and that was helpful to launch our initiative. And then we applied for it again in 2021, and we won that. So Brian and I have that both recently won those grants. And Brian, you seem like okay. So let us know if we can help you with those applications, because the nice part about the Meggers grant is that it's not like an NSF grant where it's like you're expected to produce 5 papers and all this stuff. Like the Meggers folks, if you're going to put unique content on YouTube or train teachers, and you're not sure exactly how researchy it's going to be, they're still very excited to cheer you on. That's a nice stepping stone to some of the bigger grants. So I really appreciate, as long as the recorder is running, I really appreciate how much they've been able to support our project. So I want to spend a minute to kind of talk about where the STEM coding project has been, and sort of where we are now. Where we are now is kind of into data science, but I don't want to assume everybody in the room is familiar with kind of how we started. But we won the AIP Meggers Award in 2017, and the title of our proposal was bringing the hour of code to the physics classroom. And so Hour of Code is the world's most popular computer science education website. And when I looked at it in 2016, before I wrote that proposal, I selected on science activities, and I saw almost nothing there. And so since 2017, we've been creating all these fun things. So if you go here and you click on, find STEM coding project here, you'll see there's our Pi Day activity, but most of our activities, I don't know why there's this beginner and comfortable thing, but basically in 2017, we started to create these physics of video games activities. And at the time, I kind of felt like there was a big opportunity to use classic video games to help integrate coding into physics. So Asteroids game, Lunar Lander, Angry Birds, those are all very fun games that have great physics in them. And not only can you just use it in the sense of, okay, well, let's just find a way to put computer science into this physics course in a way that sort of makes sense. It's also nice in that games like Angry Birds, or with the Lunar Lander game, where you have a little rocket supposed to land on the moon. There's ways to double check that those codes are working, right? So with Angry Birds, you can predict the trajectory and compare it to an upside down parabola. With the Asteroids game, you can check to see if you don't fire the thrusters at all, do you fall to the moon in the correct number of seconds? And so what that does is that we're trying to do something fun and interactive, right? But we're also double checking that those simulations are actually working correctly. And so a lot of the inspiration for what we're doing is not just to have fun and learn coding, but it's also to try to get students to think about using simulations and having kind of a skeptical point of view towards what the computer is doing. Because I personally, I teach a lot of Ohio State freshmen who are engineering majors, and I'm aware that someday many of them will be using sophisticated programs to do engineering work. And it's very tempting to believe that a sophisticated engineering program is always correct because of its complexity. Is a NASA engineer. He can tell you stories about how you can misconfigure those codes so that to make you think that the rockets are stronger than they really are. But that's a lot of our approach. So maintain the fun, but also connect it. Also be skeptical about the results of the program. So we've created quite a few activities. Sorry, I'm zipping through this rather quickly, but so these are all of our physics of video games activities. So Planetoids is similar to Asteroids. I'm going to talk about this in a minute. And then we started creating activities for astronomy. Many of them are also interactive, and I'll show you what I mean by interactive in a second. So let's see. So here's one of the first activities we put on our code. And so here's the code there. So I'm using JavaScript, which I know is maybe not the most popular choice in the room. But what's the nice part is that so for one, the browsers think in JavaScript. So that's nice. As you can see, I can move this little ball to the right, but if I press up or down or left, it doesn't do anything. And your job is to modify this code to get it to go in all the different directions. So during the pandemic, spring 2020, I frantically figured out how to add all these little objectives to my activities so that students could get instant feedback. So prior to spring 2020, this was just blank, and they just had to look at the code and see if it was working or not, which worked okay. But I've managed to add this to a lot of what I'm doing. So that's what we've been up to for a while. I want to highlight that we've been doing a lot of astronomy activities. So with Jamora and Daniela from Ohio State's astrophysics group. So they recorded a bunch of astrophysics activities with me, and exoplanets and black holes and things like that, all at the high school level. And so, for example, you can do calculations of event horizon and escape velocity, basically Newtonian calculations, and you can make a little code to do that. So when we do coding, we do things like, so here's this slingshot with gravity thing. So we don't just want to make it work and give an answer. We want to do things like, I can touch the screen and I can launch this object. And so we want it to be really interactive. So you can do it quantitative and you can all that great stuff, but it's also really interactive. And I'm sure you can sort of do similar things with Python. But this is the environment that we decided to use. It's called P5JS, and it's very fully featured. And the nice part about it is there's this huge community of people that are working on it. So what I want to highlight, so that's kind of where we've been, and where we're going is data science. And so we are trying to create a year-long curriculum for data science that would essentially compete with the other data science initiatives that are out there. So there's one with Stanford, there's one with UCLA, but we have some tricks up our sleeve that are going to make ours interesting and different from what other people are doing, because I don't know how to do things the same way everybody else does, so basically. So over the summer, for example, we created this activity. We call it Earth Day, and so this is now on our code. Actually, where is it? Is it up there? Yeah, data science. So that's there on our code now, and the basic idea of it is to model the climate at your location. And the question is, so Ohio is in a unique position in that climate change is very obvious in most other parts of the United States. I don't have to lecture anybody in California about climate change or the American West. I don't have to lecture people in Florida about how the extra hurricanes show up each year. But in Ohio, explaining climate change it's a little bit more difficult than it is in other parts of the country. And so what I did was I created an activity that basically you look at the climate at your location and you model it with the cosine wave, and then you add a shift to it. And the thing that you're thinking about is how many fewer days of frosty weather do I get? So if you're going to quantify climate change, instead of saying it's like 1.4 Fahrenheit or a 3 Fahrenheit change, how many fewer frosty days do you have at your location as a result of climate change? Does anybody want to guess how many fewer days it is? I can't see the chat, but in some places it's about a month that we've lost, essentially. So that's kind of the basis of that activity. But the thing I like about it is that it's one of the few activities that's on our YouTube channel in which you download the data and you analyze it with the spreadsheet. So you can do things like downloading the data and let's see if I can get to that screen. I have it all set up so you can't just jump to that screen because you want students to actually walk through it. So you can download the data, you can find the minimum temperature, you can use the min function, you can sort. Like, it just teaches a lot of basic spreadsheet skills. which doesn't seem that exciting. Like people have been saying spreadsheets for a while, and I'm preaching to the choir to some of you here. In fact, the professor at OSU that I kind of replaced, so that he taught at the regional campus that I'm at, he had a whole book on spreadsheets. And when I started, I was like, spreadsheets, never mind. But I've really kind of come around to it, because what I've seen is that all these data science initiatives that are out there, they're focusing on R, they're focusing on like making plots with Python and Matplotlib, which is fine, but R is it's a language. Python with Matplotlib is a language, and I'm sure there are some high schools that can do it. But the thing that people are familiar with, and the things that teachers that already have some familiarity with, is spreadsheets. And it'd be a shame to have a student go through a curriculum like that and to not be able to come out of it just being able to do a linear regression with Google Sheets or Excel or something like that. So that's kind of what we're trying to work for. This is one of the activities that we're working on. Another activity that we have that we recorded, I guess a year or two ago, is this. It's called Night Sky Simulator. Let's see if I can bring it up. So this is one of the astronomy activities. Where is it? Sorry, I have to search for it here. Here we go.
Yeah, I'm gonna call it right now.
So of course we have to watch an ad, but this activity I think is really fun, because the code is producing a synthetic night sky. It's producing a fake, constellation. It's doing that by using some random number generators. It's using that, thinking about the brightness as a function of the distance, that sort of thing. It's doing, my background is in astrophysics, so nowadays I do plasma physics, but I know a fair amount about stars, and so I can put that in there. And so they generate a synthetic night sky, so something to look at, which is nice. But then they download the data, and they try to see if the brightest stars in the sky are also the closest stars in the sky. And the answer is that not always, right? So for those of you in the astronomy world, you know that the closest stars are actually, fairly dim. And so this produces a nice multi-tabular data set that you can sort on and learn things about that data set. So this is another example of kind of what we think is appropriate for the high school level. Now, the new thing that we're working on that I'm happy to give you access to and things like that is this object tracker. So I promised I would talk about this new tools. How am I doing on time, by the way?
It's about 10 more minutes. We'd like to save some time for questions.
Sure, great. So I've had various versions of this in the works for probably since summer 2020. But this is the latest and greatest version. So every couple months we improve it significantly. And so in the past we would, anyway, so I'll show you some of the new features of this in a second. In 2020, during the pandemic, I was thinking about what we would do for the class, for at-home labs and things like that. And I looked at the different video analysis programs that existed, and I know there's a lot of Tracker Video folks in the audience, which is great. At the time, Tracker Video didn't work in the browser. There was Pivot, but Pivot even today I don't think does object tracking. And what's the other ones? There's some that work for iPad that do object tracking, but they didn't work on Chromebooks. And so I wanted something that would work. And the thing that I realized was that the way that Tracker Video is doing object tracking is doing it as like a sophisticated image processing algorithm, where you give it a picture of the object and it tries to track that picture as it moves through all these different backgrounds. Well, you can make the job of the algorithm a lot easier if you use a solid color background like I do here, and maybe like a brightly colored object. And so the image processing works even better. But actually, an even simpler way of keeping track of the object is just to look for the colors. And just look for, if you have a basketball, look for sort of orange-red pixels in front of a black backdrop. And so I tried it out, and it works fantastically. And so I'm going to go ahead and click this button here. And so this is so here it is in action. So it's tracking all the pixels that sort of have these colors here. So these are the object pixels, these are the background pixels. I should probably make these more black, but in any case, it works rather well. And then it does a beautiful job of tracking this object. And then when it's done, it will save a CSV file that I can open up in a spreadsheet program. So there you go. So then here we go, it pops up. Now, the thing that I love about this file is that, maybe this is a weird thing to love about it, but it only has the X and Y positions. It does not have the X and Y velocities. It doesn't automatically calculate the accelerations and things like that. So a lot of the programs that are out there, so for example, what's the one by Vernier? If there's Vernier has Pivot, and I also have this other one, video something, video physics maybe. So they automatically calculate the velocity and acceleration. So I do want to prove that it does have real numbers here, by the way. So this is just, so there we go. So it gives you nans until the object moves into this area. So it gives you these numbers, and then you can make the student sort of figure out how to analyze it. So this is sort of my analyzed version, and I was just really pleased to see that you get nice velocity data. So if you infer the velocity with a center difference or forward difference, and you can talk to the students about what the forward difference and center difference is. Like, it takes a fair amount of spreadsheet skills to kind of go through here. And the thing I really love about it is that, like, you can talk to the students about, well, why don't we calculate the velocity for this first cell? It's like, well, if we're doing center difference and we're taking the difference of this and this, that's not going to work. And so the programs that are out there automatically do this housekeeping for you, but with this, you can actually kind of make them do it, and I think that they learn a lot. And I also feel like, I've used this some in my class, not as much as I'd like to, but I do feel like when I use this in my class, my students feel like, oh, they all feel like, oh gosh, I was really supposed to learn spreadsheets at some point. Like, they feel like, I've been meaning to do this, and now here it is, and it's kind of tricky, but I feel like I'm getting the hang of it. So my feeling is that the students actually kind of appreciate that I'm kind of forcing them to do this. So our plan, so that's what we've been working on. Our plan is to try to record more. It turns out there's not a lot of videos out there that have solid color backgrounds. I'd love to have people's help in the audience to do this. There's a lot of videos out there of object tracking, but not many with solid color backgrounds. So we want to have a website that has just many different things that you can download, because you can choose this video or you can upload your own video. Now, for idiosyncratic reasons, it analyzes GIF images. So that's kind of annoying, right? Because there's not, but I created this converter program. Oh, come on. Why is it blocked? I've created a converter program. I'm going to fix that, I guess. Convert to, really? That's not good. So it's a program that will automatically convert the files. I swear, there it is. So I guess Firefox doesn't like it. So you can upload your own file, and you can upload an MOV or an MP4, and it will convert it into a GIF file. What's cool about this converter is that it does two things. One is that it automatically degrades the resolution, because you don't really need high resolution to do this kind of analysis. The main thing that you need is high frame rate. So if you have 240 frames per second, which a lot of like iPads these days and smartphones can do 240 frames per second. So that's what you really need. This is not a great video. It's kind of shaky, but I just wanted to show you that it works. So it's downgrading the resolution to something that's really small. So when you download the file, it's not a huge file. And then the other cool thing it does is that it's actually using all the different cores on your CPU to do the conversion. So it's super fast, and it works really well. So I'm really proud of that. I guess it just doesn't want to work on Firefox, it turns out. So that's a fun thing that's helping on it. So So we're trying to make this part of a full year-long curriculum for data science. And I think the computer science movement, computer science is really great, and there's been a lot of effort in putting more computer science in classrooms, offering more computer science classes. In some ways, data science is the new exciting thing that the people are excited about now. But the problem is that most of the people that are doing high school data science, they're from, I don't know if this is a problem, but they're from like a social science background, so they're bringing their lens to it. And maybe the tragedy of it is that part of the reason why they're doing data science is because there's this backlash now against Algebra 2. Most of the reason that Algebra 2 is there, I think, is because it bleeds into physics. And so there's a backlash against Algebra 2, and so they're replacing the things that would be helpful for physics, they're replacing it with stuff that's for data science without a physics emphasis. And I think it's fun to sort of create stuff that fills that need. And the last thing I want to say is that this year-long data science curriculum, a cool part about it is that there exists an industry credential for Excel, which is not extremely difficult to complete. Like, it seems very doable to high school students. And so the difference between what we're doing, and this is part of how we address equity and part of how we are going to reach people that wouldn't otherwise be interested in data science, is that they're going to learn all this fun data science stuff. They're going to do their own experiments. They're going to have more of appreciation of how important it is to make sure the experiment is well designed and everything's all steady and all that stuff. But they're also going to go away with this industry credential, which is really valuable. And so for a lot of schools that a lot of schools might not necessarily think of doing data science, but because of that option, I think they might give us a second thought. And none of the other initiatives are going to connect things to industry credentials. So, you know, UCLA's, they use R. There exists an industry credential for R, but it's super tough to pass that test. Stanford is using Python and Matplotlib. Pretty difficult to pass the industry credential for Python. And so I think that this combination of physical science, I showed you environmental science with Earth Day, this combination is something that I think is going to be really fun. And so we're integrating this sort of thing into our training, the training that we do. This is for last summer, but we're going to offer it again this next summer, and I hope we can actually reduce the cost. But this is the summer training we do, virtual training. It'll be about the same dates there. So hope I didn't go over time, but I'd love to get people's questions. Thank you.
All right. Questions? One thing that you might address, there was a little bit of talk about this in the chat about some of the other tracking software working in browsers, and you commented on why that was important, but anyway, if you want to react to that at all.
All right, I agree with Brian that the tracker, I'm excited that it works in the browser. I think janky is a fairly good word for it. It could be better, but it is there finally, which is good. How do you access? So Nick, I don't know which questions I should address first here.
Whatever you want to address first.
Okay. I didn't know if linear video analysis worked in the browser. I thought that was Pivot. It only worked in the
Actually, we've been using it since basically the pandemic. Basically because it works on most platforms without any installation. It also does do video tracking as well. Maybe not as beautifully as yours does. So I can see the usefulness of that. And I also completely agree, Chris, that having the automatic computation of the velocity and acceleration is destructive, I think, to the students. They really do need to work through that themselves, and there's always some confusion about that. So definitely I'm agreeing with your observation there.
I'll chime in to just sort of third that point. I've used Tracker, and when sort of tracking real world objects, oftentimes the velocity and acceleration data is near useless when it comes out of Tracker. So anyway, yeah, I would much rather have something that didn't give them that option.
I also like, Chris, on your interface, how much easier it is to get it to a spreadsheet. You can do that from Tracker, but it's got more steps and you're never quite sure what to do right. But just exporting to a spreadsheet is wonderful.
What is a it starts with an A.
Yeah, there's some sort of proprietary. It's an ASCII text file that you have to deal with from Vernier, and then get that into a spreadsheet somehow. So that's nice. One thing I want to say to what was Ernie was saying is that it is always better to do a solid colored background when you're trying to track object. Like, it always was better to do it that way. So like, we literally bought these black poster boards to give to our students and give them bouncy balls, things like that. So whatever program you're using, it's going to work better. I mean, did you have a question?
Yes, I had a question regarding your background. Why did you take, I mean, the tracker, why did you take the first frame as your background and subtract every other frame from that frame? So then you can basically see the object is going to get tracked in the frame that you're looking at. Why do you need the solid color?
Right. Well, so the thing you have to realize is that as the object moves, the lighting that's on it is going to change. And so it's not going to look the same as it initially as it will, a few seconds from then. And so it'll work, Tracker video. I mean, we've all seen videos from Tracker video where it just beautifully just latches on and just, does it. But the thing is, the fact that it can do that is great, but the thing is that it needs to be able to do that like without a lot of tinkering. And the thing that requires less tinkering is if you focus on the colors. I really want to write an article for the physics teacher, an article for American Journal of Physics, just sort of like, here's how you might do this, because I'm not trying to make any money off of this. I just want to, the thought occurred, it was shocking to me that no one had tried this before, seemed to not try it before.
Okay, thanks.
I do want to say, if anyone would like to collaborate with me on STEM coding stuff, we have a nonprofit now. We have our own learning management system now, which has over 1,000 accounts on it, things like that. So we're not like too big to fail or anything like that. But if you want to have an impact on teachers, and if you have this much time, that you want to have this much impact. I'd love to collaborate with you.
There's a question from Charles Allen in the chat. It says, is there any spreadsheet out there these days that enforces array structure so that cells can't get out of sync? Rows added that accidentally get the correct formulas, etc.
Is there any spreadsheet out there? I'm not totally sure how to interpret that question. I mean, maybe I don't know enough about spreadsheets, incorrect formulas. I mean, the spreadsheet programs, I mean, the guardrails are definitely off. And that's kind of the whole point of it, I think. But there's Excel is slightly different than Google Sheets. There's a thing called CodeApp people are using sometimes. So I don't know. I'm not sure I'm doing a great job answering this question. Sorry.
All right, Brian.
So Chris, if you gave this formal definition, I'm sorry that I lost it while I was interacting with people in chat. But so when you talk about integrating data science into our physics classes, is it literally just a matter of rebranding the analysis we're already prone to doing as data science, or is there new sorts of objectives we need to start thinking about integrating into our classes?
Yeah, it's a good question. I mean, I think that I think that what it means is that if you spend a lot of your class period showing students how to do linear regression, you don't have to feel bad about it, right? Because it's a life skill, and it's part of physics. I mean, the other day somebody asked me like, "Well, aren't you just adding a little bit of computer science into physics?" And I was like, "Excuse me, physics and computer science have gone hand in hand. Like, we invented email at a particle accelerator and the internet. So computer science and physics have never been separate, really. So on some level, it's labeling, yes. But we are trying to get these full year-long data science courses. That's ultimately what we're trying to do. A big challenge with that is that physics teachers are not allowed to teach data science in a lot of states. So in Ohio, for example, math teachers can teach data science. That's part of why it's an exciting thing to do, is that you don't have to have computer science credentials to teach this class, which clearly has a lot of computer science in it. But computer science teachers can teach data science, but physics teachers cannot. So I'm thinking about doing a petition to try to get folks like Computer Science Teachers Association, folks like code.org, to try to declare that science teachers should be able to help teach data science if they would like to. I don't know why it hasn't occurred to them before. They seem to be okay with letting anything fly in terms of, computer science count for foreign language, count for math, counts for science. Well, why not let science teachers teach data science then?
With as much cross-pollination as we have with physics teachers filling in for math, or chemistry teachers filling in for physics, like, they're all coming from the same pot of skill set anyway.
Right.
Yeah, it would totally make sense.
Yeah, or just teaching math in our actual physics course when the students' algebra skills aren't great. Brian, I think what you're doing is great because in a few years, the banks and the Googles of the world are going to be demanding people who know how to do quantum computing, and they're going to say to themselves, where do we find these people? And so you guys, I think, are ahead of the curve. I mean, part of your funding comes from the banks, essentially, right?
Correct. Yeah, from Voya Foundation is saying, well, we know we're going to need this talent pool later. Talking with some folks after the recent AAPT winter meeting, where there was this sort of emergent quantum focus. I don't think it was exactly planned, other than there was a lot of interest in it. There was kind of this consensus of, we know this is going to be necessary. It's a hard sell right now because it's not necessary now, but we want to figure out how to do it now so that when it is necessary, we know how to, that what we're going to roll out is useful.
Nick, I had one other, thanks, Brian. I had one other thing I wanted to ask the room is that, do people know Mark Hannum from AAPT? I know Brian knows him. He's a great guy, very on board with coding and physics and all that stuff. So he sent out a survey a couple weeks ago about if people were interested in a Jupyter workshop. And I think he did have a lot of good responses from it. He actually shared some of the survey responses with me. And we started talking about, like, would it make sense to do an in-person workshop or a virtual workshop? But he was trying to connect the dots to try to do some sort of extended Jupyter workshop, not just like a half-day workshop at the summer APT, but something more extended. So I just want to put that out there of, there seems to be a demand for this. And Mark even thinks that some of the teachers that I've worked with, they like my stuff, but now they want to move on to learning Jupyter notebooks. So I just want to put that out there. If this is something that we could potentially help Mark with, is maybe this is something we could talk about on the Slack channel. So anyway, just leave that as food for thought.
All right. Well, our hour is up, so let's thank our two speakers again. And as usually happens, we'll leave the room going, but I'm going to stop the recording, and we thank you all so much for coming.